Welcome to our Fermi problem series. Growing mountains and rising skyscrapers. The sky is not the limit. Let's take a moment to appreciate the power of Fermi calculations in nature and engineering. If this is your first time visiting this channel, the videos in the Fermi problem series are presenting solutions to exciting problems which are excruciatingly hard to solve by exact and often not necessary calculations. Ancient Greeks thought that their 12 gods were residing on Mount Olympus. Mount Olympus is the tallest mountain in Greece with an elevation of 2,917 meters. The first time I visited Greece, I was in awe after seeing the impressive mountainous terrain of its mainland. Even many of the Greek islands are the peaks of submerged mountains. Then, I learned that mountains in Greece are mostly fold mountains, formed by the collision of two tectonic plates, the African and the Eurasian plates. More precisely, the African plate is subducting beneath the Eurasian plate. Mount Olympus is such a fold mountain made of sedimentary rock layers uplifted over millions of years. About 4,450 kilometers away towards the east, one can find Mt Everest, the highest peak of the Himalayas mountain range with an elevation close to 8,849 meters. The Himalayas are also fold mountains created by the collision of the Indian plate and the Eurasian plate, which push Mt Everest upwards about 1.6 millimeters every decade. If fold mountains are the result of pressure, given enough and continuous, uninterrupted pressure, how high can they elevate on Earth? It is intuitive that if we keep stacking weights on top of each other, eventually the arrangement will be so heavy that the lower layers will not be able to support the load. As a result, this limitation on the load places a limitation on the height on any construction, human or non-human made. Consider a uniform structure of any shape with base area A and height h. If Pc is the compressive strength of the material used to make the structure, given in units of pressure, and P the pressure on the base created by the load, the structure survives as long as Pc is greater than P. Once the inequality reverses, the structure collapses. Obviously, the critical case is Pc equals P, which determines the maximum height Hmax of the structure. The pressure created by the load can be computed by its weight and base area. In particular, P equals weight over base area, or P equals mass times acceleration of gravity over area. Next, the mass of any structure can be expressed in terms of its density. Mass equals density times volume. The volume depends on the shape of the structure. For a right cylinder, volume equals base area times height, and for a right cone, volume equals 1/3 times base area times height. Taking into account all previous information, and after substituting in the critical case, we find that Pc equals maximum height times density times acceleration of gravity for a cylindrical structure, and Pc equals 1/3 times maximum height times density times acceleration of gravity for a conical structure. Notice that these expressions are independent of the base area. How large the construction is in the horizontal dimensions is irrelevant. Solving the last equations for the maximum height of the structure, we find maximum height equals Pc over the product of density and acceleration of gravity for a cylindrical structure, and maximum height equals 3 times Pc over the product of density and acceleration of gravity for a conical structure. Notice that the maximum height is proportional to the ratio of the compressive strength over the density of the material, not just its strength. Also notice that, for the same material, the conical shape allows the structure to go 3 times higher than the cylindrical shape. We can now apply the results for the maximum height in nature and engineering. The first application will be on the mountain elevation. The second application will be on the limitations of the height for a skyscraper. And finally, we would like to know if this computation can give us an insight on the maximum height of a tree. Mountains have conical shape. Mount Olympus is made of sedimentary rocks, with limestone and dolomite be the dominant ones. Limestone has a density of 2,700 kilograms per cubic meter and a compressive strength of 150 to 200 megapascals. Dolomite has a density of 2,850 kilograms per cubic meter and a compressive strength of 32 to 300 megapascals. The variation of the strength is due to various factors such as grain size, mineral composition, and presence of fractures. For our Fermi calculation, conservatively, we will assume that Mount Olympus has a density of 2,850 kilograms per cubic meter and a compressive strength of 150 megapascals. Hence, applying the formula for the maximum height of a conical structure, we find a mountain of limestone and dolomite like Mount Olympus can elevate up to 16 kilometers. Mount Everest has a more complex composition. At the summit is made of sedimentary rocks in which limestone dominates. Just below the summit is a distinctive layer known as the yellow band, a mix of shale, sandstone, and limestone. The lower portions of the mountain consist of metamorphic rocks. In the middle, marble, quartzite, and schist are the dominant rocks, while, as we go closer to base, granite, gneiss, and migmatite are the dominant rocks. Although the composition of Mount Everest is very complex, once we look at the densities of rocks, we realize that all of them are in the range of 2,600 to 3,000 kilograms per cubic meter. Similarly, all compressive strengths are in the range 50 to 350 megapascals. Hence, the average density and compressive strength of Mount Everest are similar to those of Mount Olympus. Therefore, the limit of 16 kilometers that was derived previously is good estimation in this case too. In fact, it is a universal limit for all mountains made of rocks. Olympus Mons is a massive volcanic mountain on Mars. It has the size of Arizona and a local relief above plains of 26 kilometers. As such, it is the tallest mountain in our solar system. Olympus Mons is made of Martian basalt. The Martian basalt is like the basalt on Earth, but with higher content on iron and lower content on aluminum. Its density is 2,900 to 3,100 kilograms per cubic meter, and its compressive strength 100 to 300 megapascals. In other words, they have similar ranges with the Earth rocks. However, the acceleration of gravity on Mars is 3.73 meters per square second. This implies that our formula predicts a maximum elevation of 42 kilometers. Let's switch to skyscrapers. Short high-rise buildings are usually cylindrical. However, as modern skyscrapers attempt to break records, they are built with setbacks at various heights or other design innovations, so they approximate a conical shape. With respect to materials, they are built with steel or reinforced concrete frameworks. The density of steel varies based on the alloying constituents, but usually it ranges between 7,750 and 8,050 kilograms per cubic meter. Its compressive strength varies from 250 to 1,500 megapascals. The density of concrete varies considerably based on the application. However, the typical structural concrete used in buildings has a density of 2,400 kilograms per cubic meter. Similarly, concrete used in high-rise buildings has a compressive strength of 40 to 100 megapascals or higher. Conservatively, I will select the following values. Notice that steel is better material than concrete, since it has a larger ratio of compressive strength over density. More precisely, for conical shape, The exact maximum heights are 15 kilometers for steel and 10 kilometers for concrete. Therefore, the challenge in constructing taller skyscrapers is not coming from our construction materials. Although other kinds of strength beyond compressive strength is an important issue, engineering must overcome additional serious difficulties regarding stability, which are related to the quality of the ground, wind, earthquakes, etc. Let's now move to the height of trees. Galileo suggested that no tree could grow taller than 300 feet, but he did not know of the coast redwood in California or the eucalypts in Australia. The tallest tree today is Hyperion, a coast redwood located in the Redwood National Park in California. Its height is 380 feet, 9.7 inches, or 116.07 meters. It was discovered in 2006, and it is estimated to be 600 to 800 years old. In various past sources, there are claims of taller trees with heights up to 480 feet, but researchers have raised doubts about the accuracy of the measurements. The trunk of the tree, which carries the majority of the weight, has a cylindrical shape. For convenience, I will use eucalypt as the tree for the calculations. The wood of the denser varieties of eucalypt in wet form has density from 800 to 1,200 kilograms per cubic meter. The compressive strength in dry state is 40 to 90 megapascals. However, in wet form, the strength drops 25% to 50%. Let's assume a density of 1,000 kilograms per cubic meter and a compressive strength of 40 megapascals. Then, our formula predicts a maximum height of 4,000 meters. If this order of magnitude was true, then there should have been many reported trees with immense heights. However, this is not the case. Therefore, we must conclude that this mechanism, that is crushing under its own weight, is not the main mechanism that sets the limit on the height of a tree. A tree is a live organism. As such, there are many biological functions at work to ensure its well-being. Stricter bounds are set by these functions. And with these comments, we have concluded today's video. I hope you liked the Fermi problems on the maximum height of natural and human-made structures. If you did, please subscribe to my channel to encourage the creation of more content like this. Thanks a lot for your support.